Hello students, welcome to Saraswat classes. Now, today we're going to discuss a topic which is related to how to predict a molecule is optically active or not. Okay, and this can be done by knowing the concept of elements of symmetry. Now, according to group theory, if a molecule has any of these symmetry elements present within it, say plane of symmetry, uh, center of symmetry, alternating axis of symmetry. If these three are present, then the molecule is superimposable with its mirror image. So, what is the other concept? If the molecule has none of these elements of symmetry but only has the simple axis of symmetry, then it is not superimposable with its mirror image, or we can say it is optically active. Okay. So there are two ways of finding out whether a molecule is optically active. Either you construct the molecule using ball and stick models, make its mirror image and try to superimpose them and try to find out whether they are optically they are superimposable or not, or else you look for these symmetry elements within the molecule. That is what we are going to discuss today over here. How to find out these elements of symmetry. Now, let us first discuss what is this plane of symmetry. Okay. So for that, let us take some alphabets. Okay. Say A, B, C, D, E, F, H, I, J, K, and let us think that we have to pass a line along which we will think that there is a plane lying on it, so that these molecules can be divided into two equal halves. So that if we think and you pass a line as I am showing for the letter A, so this will be called as sigma V. That means the plane of symmetry is lying vertical with respect to the object that I am trying to, or letter that I am trying to divide in two equal halves. Similarly, for the letter B, this is called sigma H. Okay, again for C, sigma H, for D, sigma H, for E, sigma H, none for F, none for G. For the letter H, we have a sigma H and also a sigma V. Similarly for I, sigma H and sigma V, but none for J, none for K also there is a, okay, so we can say there is a sigma H over here. Alright. So ideally, a plane of symmetry is a plane, one can define like that. It is a plane such that if a line from any element on one side of the plane is drawn perpendicular to the plane, and the line is extended to an equal distance on the other side of the plane, an identical element will be found. At the end of line. So that would be the perfect definition of a plane of symmetry. Or to put it more simply, we can say one half of the molecule is the mirror image of the other half, and the plane of symmetry being the plane of the imaginary mirror. So let's look at this molecule over here. Now if I pass a line, the dotted line, which I'm calling as sigma V, as you can see over here. So this particular molecule, even though it is having these stereogenic centers which were designated using this asterisk, so even though it is having optically active centers, because it is having a plane of symmetry passing through it, we will say that this is going to be, as a whole, the molecule will be optically inactive. Okay. So let us take a few other molecules. Okay. Suppose we were given a molecule like BeCl2. Alright. Now if you imagine all these atoms to be as spheres, so one can think that this is almost like a cylinder. Okay. With the B being present in the middle. Alright. So one can think that there is a plane of symmetry passing vertically like that, and there will be infinite number of planes of symmetry which are horizontal that would be dividing this symmetrical the cylinder into two equal halves infinite times. So we will say it has infinite number of sigma h, and there is only one sigma v. Similarly, let us take another molecule which is, let's call it the BF3, which is trigonal planar, where the F are lying at the vertices of the triangle, and so this is how the arrangement will be. Now you can think, I'm using this green dotted line, so this molecule, if you imagine the ball and stick diagram where you're considering each of these atoms to be as spheres, okay, so there will be a sigma plane of symmetry passing like that. So this is again your sigma v, there is another sigma v like that, there is another sigma v like that. So we're just using these molecules to understand the planes of symmetry that can be there in the molecule. Okay, and obviously there will be a plane of symmetry which is sigma h. If you can imagine these dotted orange lines, so this will be the plane of symmetry that will be lying on this framework, and that will be our sigma h. So there are 3 sigma v's and 1 sigma h present in a BF3. Okay, so this is how we can imagine plane of symmetry in different molecules. Okay, we can extend the idea to benzene also, in which this is the frame up of the molecule and this is the delocalized pi electron cloud. Okay, and now if you try to imagine, we will be saying that there is a sigma plane like this which will be passing through the alternate carbons. Let us call this as sigma d, means sigma diagonal, and let's consider these green dotted lines. Okay, and these will be called as sigma v, whereas we know there is a pi electron cloud p lobe on the top and a p lobe downwards, so there will be a sigma h that will be lying exactly on the molecular framework of the carbon atoms forming the molecule. Okay, so this is how we find plane of symmetry in molecules. Okay, and one can extend the plane of symmetry to molecules that will be having optically active centers. Even though they are having optically active centers, if there is a plane of symmetry, then it will be dividing the molecule into 2 equal halves. Now let us consider center of symmetry. So again we are taking a derivatized cyclobutane as the example, and suppose we place one carbon here. Here is the hydrogen, this is the CH3, and there is a C2H5 oriented like this. Sorry, this is your C2H5, and we have another carbon as shown, and there is a C2H5. This is the hydrogen, and that is the CH3 over here. Now, a center of symmetry is basically a point such that if a line is drawn from any element, okay, to this point and then extended an equal distance beyond this point, another identical element will be found at the end of this line. So this is what we will call as the center of symmetry. Okay, let us now consider alternating axis of symmetry. Okay, and basically we are discussing here the fourfold axis of symmetry. So for that we are taking an example of this molecule. Again, one can say this is a derivatized cyclobutane ring. So we have a C, there's a H, so this is C2H5, this is the CH3, okay, let me make this a little more tilted so that we can have some clarity. So there is a C and then there is a H, there is a CH3, we have a C2H5, and now we have some more asymmetric centers. There is a C2H5, there is a H, this is the CH3, again we have the C2H5, CH3, and this is the H. Now if we were to rotate this molecule, okay, by 90 degree, so if we were to rotate the molecule by 90 degree, what we will get is going to look like the following. So we have a C, then we have C2H5, this will be my CH3, That is going to be the H. This will be the H. That is going to be the C2H5. And this is the CH3. Now let's imagine another one. So this is the H. So this is the CH3. And that is the H. Okay. This is how it will look. Okay. All right. And now if you were to invert this molecule upside down, okay, then what you are going to get will be exactly the molecule that was written before. And this will be the one. All right. So somehow this is not pasting over here. Let me try it again. Control V. All right. It doesn't paste over here, so let's not get too much worked up with that. So if I say this molecule to be as A, so what I will get over here is going to be the molecule A. So this is what is meant by the alternating axis of symmetry. Now since you are making a rotation over here by 90° and then you are reflecting this molecule over this mirror plane, so basically the alternating axis of symmetry over here is now the S4. That is why I said it is called as fourfold axis of symmetry. So a n-fold axis of symmetry is an axis such that when the structure possessing this axis is rotated around the axis by an angle of 2 pi by n and then reflected across a plane at right angles to this axis, which is the mirror plane, it gives you the identical structure. All right. Now at last we will be calling what is a simple axis of symmetry. Okay. So suppose we have been given this molecule. So there is a carbon over here. There's a carbon over here. and that is your C2H5. This is your hydrogen, and that is your CH3. Okay, this is the hydrogen, that is the CH3, and this is the C2H5. So if I were to rotate this molecule along this axis, which is obviously, if I take the degree of rotation, it is going to be, theta value will be equal to 180. So over here, if I call this as to be molecule A, now after the rotation is being done, it will actually reproduce the molecule A. So a simple axis of symmetry we will define as an n-fold axis of symmetry such that when a structure possessing this axis is rotated by an angle of 2 pi by n, around this axis, another identical structure is produced. Okay, now, so in this lecture we will be discussing optical isomerism due to asymmetric carbon atoms. Okay. So a simplest source of dissymmetry in any organic molecule is when the carbon atom is attached to 4 different groups. Okay, which means a molecule of the type C, A, B, C, D, where A is not equal to B, B not equal to C, and C is not equal to D. As simple as that. So a very simple known example of this kind is a lactic acid, which can be written as CH3, C. This is the asymmetric carbon joined to OH, a hydrogen, and a carboxylic acid group. Okay. Now, in order to stereochemically represent this molecule and its mirror image, we will follow some rules which are known as Fisher rules or Fisher projection formula. Okay, and what is it? Say rule number 1, So when you are talking about asymmetric carbon, okay, we know the sp3 carbon is having tetrahedral structure. So say this is one of the bonds, and this is the other one, another one, and this is the other one. Okay, so this is A, let's say B, C, and D. Now, according to Fisher, if you want to represent this molecule in a Fisher projection formula, one has to imagine that there is a vertical line like that, okay, and there is a horizontal line like that, okay. So where these two lines meet, we have the tetrahedral carbon over here, okay. And so any atom or group that is lying on the vertical line are basically lying away from you. Okay, that means they are lying behind the plane of this paper on which I'm writing. And the groups that are written on the horizontal line, they are facing towards you. So another way of showing this will be using a flying wedge representation, in which we can say that this is the carbon and these thick bonds, okay, means they are looking towards you or facing towards you, projecting out of this paper that I'm writing on, and the dashed lines are indicating they're lying back or behind the plane of this paper. Okay, so this is what it means. Some are D and B are out of the plane of this paper, and A and C are behind the plane of this paper. So that is how you represent a tetrahedral molecule, basically, according to Fisher. Now, so according to Fisher, say rule 1, interchange of the position of 3 atoms or groups at a time are allowed. Which means that if you do this operation, then that won't change the stereochemical information that is within the molecule. So what it means, if I change from the position of B to C, C goes to D, D goes to B, the molecule that will be generated over here, so if I represent it in the following manner, these two representations, which is Roman 1 and Roman 2, they are identical. If I were to repeat the operation again, so D goes in here, C goes in here, B goes in here, and A remains fixed, then also the molecule 3, 1, and 2, they are all identical. As you can see, if I repeat the operation again, that is the rotation of the groups, I will be converting 3 to 1. And in none of the cases I've broken any bond. I've just rotated these groups. Okay. In fact, I can consider I basically rotated this bond. in an anti-clockwise manner. Okay. You can think that this is a steering wheel, all right, something like that. Steering wheel of a car, where the position of the A is fixed, and you are basically interchanging the position of the other groups. So this is suppose your B, this is your C, and that is your D. So you can go either in the anti-clockwise direction, you can go in the clockwise direction, sorry, or you can even go in the anti-clockwise direction. But in a clockwise rotation, B will always be followed by C, and C will be followed by D. And the anti-clockwise direction, B will be followed by D, and D will be followed by C. Okay, so that is what it will happen. And number two, if we interchange position of two atom or groups at a time, in this an enantiomer will be generated. So this is not allowed. Okay, while writing molecules in Fischer projection formula, you cannot interchange the position of two groups at a time. 3. So one can easily visualize this if we were to say this is A, this is B, this is C, this is D, and you were to interchange the positions of these two groups. Okay, and let's compare. So if you compare, you will see that if I call this to be as 1 and that to be as 4, 1 and 4 are actually mirror images of each other. Okay, so they're enantiomers. Now, rotation of a molecule by 180 within the plane of paper is allowed because it generates the same molecule. As we can see over here, we have A, B, C and D. Now if I were to turn the whole molecule by 180, okay, so this is a 180-degree rotation within the plane of the paper. All that will happen is that A will go in place of C, B will go in place of D, and now if you want to say this is molecule number Roman 1 and this is 5, if you were to go from 5 to 1, then also that is possible. And how one can do that? By simply say, let's go from, do a rotation of 3 groups at a time like this, then that would generate. So anything that we can generate or reproduce back by interchange of the groups 3 at a time, that means the stereochemical information has not been lost. Molecule remains the same. Okay. So this is your A, and this is your C, and that is your B, and that is your D. And now if you want to do another rotation like that, that, and that, you're basically going from, say this is 6, okay, to molecule 1. However, क्या रोटेशन 90 डिग्री में पॉसिबल है? नहीं. Rotation of molecule by 90 degree is not allowed. क्यों allowed नहीं है? देख लेते हैं. If we do it, अगर हम इसको करते हैं, so this is A, this is B, this is C, and this is D, and you do a 90 degree rotation, then what will happen over here is A goes to the place of B, B goes to place of C, C goes to place of D, and D goes to place of A. Now think, in reality, A was behind the plane, C was behind the plane, whereas the B was in front of the plane and D was in front of the plane. Now if you were to do a rotation by 90 degree within the plane of the paper, you're basically converting and bringing A above the plane, which is incorrect. Stereochemical information is being lost, and C above the plane, and you're pushing back D and C below the plane of the paper. D and B below the plane of the paper, which is not correct. Okay, and so it is not allowed. Flipping the molecule, that is lifting it and placing, lifting it off the plane of the paper and then placing it, actually generates the enantiomer, and which is also not allowed. So the flip, which will reproduce, or which will produce, sorry, a molecule like this, now this is not allowed, because again it is regenerating the enantiomer. Okay. So basically, molecules which are non-superimposable mirror images of each other, they are called enantiomorphs or enantiomers, also known as optical antipods or antimers. And these will be ones that would be rotating the plane of plane polarized light in opposite directions but have the same value of specific rotation. Okay. That should be kept in mind. Now, I'm going to summarize some symmetry designations over here. Let's know what terms we will study, what things are present. So you might get a assertion reason question from here, that is statement based questions. And let's say optical activity. So what is that? So over here, if we are saying a molecule is symmetric, alternating axis of symmetry, we will say present. Okay. Simple axis may or may not be present. And that would be optically inactive for a disymmetric molecule, especially allenes, pyrines, okay, biphenyls, may or may not be present. And these will be usually active. Some things that we have discussed before. Asymmetric, again it is absent here, absent, usually active. Okay. One more thing, one-fold axis of symmetry. Basically means plane of symmetry. Okay. Whereas the two-fold alternating axis of symmetry corresponds to center of symmetry. So these are the two things that should be kept in mind. So any molecule that has a center of symmetry, we can say easily it has a two-fold alternating axis of symmetry. Any molecule that has plane of symmetry, we will say it is having one-fold alternating axis of symmetry. Okay.